Welcome dear students. In this video we will learn about some basic concept of electron transport chain and protein motive force. Before you start to learn these two topics in details, you must remember the basic concepts. In my subsequent classes I will discuss about this electron transport chain and protein motive force in more details. So we will start from this summary. I have mentioned that during the glycolysis we have got 2 ATP and 2 NADH molecules. NADH molecules are the high energy electron carrier. Now from the pyruvate to acetyl-CoA we have got 2 NADH molecules, and from the acetyl-CoA to 4 carbon dioxide, that means in the TCA cycle we have got 6 NADH, 2 FADH2 and 2 GTP that ultimately exchange to 2 ATP molecules. Now if we summarize this whole net gain, we will get the 4 ATP molecules total from 1 glucose molecules in these 2 cycles, and 10 NADH molecules and 2 FADH2 molecules. This is the net gain from glycolysis and TCA cycle. Now these 4 ATP molecules that we have got is actually different from that we will get from oxidative phosphorylations, the ATP molecules. So this is totally different from these oxidative phosphorylations, because this type of ATP generation is called substrate level phosphorylations and this is called oxidative phosphorylations. Now the main important 2 molecules are these NADH and FADH2 that will play a direct role in the electron transport chains. So I will start this video with 2 reactions. That is, this NADH plus H plus will react with oxygen molecule and will generate, it will actually oxidize and will generate water molecules. The ultimate acceptor, electron acceptor in this electron transport chain is the molecular oxygen. But the important fact about this reaction is the delta G. The Gibbs free energy of this reaction is minus 52.6 kilocalorie per joule. Kilocalorie per joule. Mole, sorry. So from this Gibbs free energy or delta G, we actually know that as it is a negative, that means this reaction is spontaneous in these directions. It doesn't require any energy. This type of reaction is called exergonic reactions. Now when this FADH2 get oxidized in this electron transport chain, FADH2 with the molecular oxygen, it will generate FAD and water molecules. The delta G of this reaction is minus 43.4 kilocalorie per mole. In my subsequent classes I will also describe or discuss about why these 2 reactions have different Gibbs free energy. So this is all. So if we calculate the value of this reaction energy, we will get that there are 10 NADH molecules. So we will multiply this value with 10 and we will multiply the delta G value with 2. If you calculate, you will find that approximately 613 kilocalorie per mole energy you will found by this oxidation of these 2 molecules up to the glycolysis and TCA cycles. And do you know the chemical bond energy that is present in 1 mole of glucose? 1 mole of glucose is 686 kilocalorie per mole. You have to understand this. 1 mole of glucose contain the chemical energy, chemical bond energy is approximately 686 kilocalorie per mole. So if we calculate the value of these oxidation reactions and the value of the chemical bond present in the 1 mole of glucose, you will find that approximately 90% of the energy actually restored from 1 mole of glucose. So this glycolysis and TCA cycle is very energetically efficient. Now I will show you the basic idea about the electron transport chains. We know that this TCA cycle and electron transport chain and all these things actually happens in the mitochondria. So in the mitochondria there is 2 membrane. The membrane where these all electron transport chain components are present are called inner mitochondrial membrane. Inner mitochondrial membrane. Okay, in this mitochondrial membrane there are 4 complexes are present that actually take part in electron transport chains. Let's suppose this is the complex 1, this is the complex 2, this is complex 3, and this is complex 4. These 4 complexes take part in this electron transport chain. So let me write, this is 1, 2, 3 and 4. I will not go into details of the structure and components of this each and every complex. In my subsequent classes I will discuss about this in more details. Now the basic idea is that the complex 1 is called NADH CoQ reductase. The name of this complex is CoQ reductase, and the subunits, because this complex are multi-subunit molecules that actually very large in size or structure, they contain approximately greater than 40 subunits. The first complex 1 contains, and each and every complex have many different type of prosthetic groups, that means electron carrier. They carry this electron from this NADH and FADH2 to the ultimate to reach into the molecular oxygen. Now complex 2 is known as succinate CoQ reductase. These molecules have approximately 4 subunits. Complex 3 is known as CoQ cytochrome C reductase. It has 11 subunits. And complex 4 is known as cytochrome C oxidase, and contains 13 subunits. So these are all 4 complex, and in the electron transport chain there are 2 routes by which electron can be transported. The first route is from complex 1 to complex 3, then complex 4. The another route is complex 2 to complex 3 to complex 4. So when electron flow from complex 1, it actually bypass the complex 2 and reach to the complex 3 and complex 4. The same is true when electron transport from complex 2, it will actually bypass the 1 and it actually go to the 3 and 4. So this is the basic idea of this electron transport chain. Now you have to remember one fact. Yeah, the name also very easy to remember, because you know that this complex 1 actually oxidized NADH. So NADH actually first and actually reduced a ubiquinone called CoQ. So it is called CoQ reductase. The same is true for complex 2. This is called succinate, because here succinate is actually oxidized to fumarate. I have already discussed about in my TCA cycle that succinate to fumarate, the reaction is performed by succinate dehydrogenase. This subunit, this succinate dehydrogenase subunit is actually present in this complex. So succinate dehydrogenase convert the fumarate, succinate to fumarate, and it generate FADH2. Then this FADH2 actually release its electron and it actually carried out. So CoQ also reduced. So this is called succinate. This succinate is actually get oxidized and CoQ gets reduced. In the complex 3, CoQ gets oxidized, but cytochrome C, a protein, in this electron transport chain there are so many cytochromes are present. Cytochrome C, cytochrome C1, cytochrome B, cytochrome A1. So there are so many different type of cytochromes present, but the basic structure of this all cytochrome proteins is the presence of heme prosthetic group. This is called heme prosthetic group. This heme prosthetic group contains 4 porphyrin rings, and it in the middle there is a iron group is present, iron that is in the Fe3 plus conditions, and this iron actually when takes the electron it becomes Fe2 plus. So the oxidation and reduction takes place in the cytochrome also. So CoQ, here the complex is CoQ gets oxidized, the CoQ that comes from the second or the first complex, okay, and the cytochrome C gets reduced. Now in the fourth complex, the cytochrome C gets oxidized. This is a simple fact, and the ultimate in the complex 4, the oxygen gets actually reduced to make water molecules. So the basic concept of this electron transport chain is a term you have to remember, that is called redox potential. Redox potential, or it is actually equivalent, if you remember, as a electron affinity. Electron affinity. For your simplicity, forget about the name of this complex or everything. Just remember, just try to understand that suppose there is 4 molecules are present, or you can say electron or electron acceptor or donate, so they can transport electron. So let's suppose there are 4 molecules are present, A, B, C, D. Okay, if electron wants to move from in one direction, because in the electron transport chain the electron move from unidirectional, and this during this unidirectional movement electron doesn't require any energy, and this type of movement of electron in the electron transport chain is called downhill movement of electron. Downhill movement of electron, and electron always go in unidirection. That means it will go from 1 to 3 to 4, it will not return. It will go from 2 to 3 to 4, it will not return. So this unidirectional movement and the term downhill, what does it mean? To understand this, you have to understand one term that is called redox potential, or easily you can remember electron affinity. So let's suppose a electron is try to move from complex A or molecule A to B to C to C to D, ultimate etc. Let's suppose. So if this electron try to move in one direction from A to D, the redox potential or the electron affinity of this molecule should increase as the electron will flow just before the immediate. What does it mean? Okay, I will give you some very easy example so you can understand. Let's suppose the redox potential is of this A molecule is 200 millivolt. The electron affinity is 200 millivolt, plus 200 millivolt. Let's suppose it could be minus also, but let's suppose this is a plus 200 millivolt. The A molecules has a redox potential. Now if the electron wants to move or transport, because it is called electron transport chain, if the electron wants to transport from A to B, not from B to A, then the redox potential or the electron affinity of this B molecule should be higher than this A molecule. They should be anything greater than 200. Let's suppose 300 millivolt. And the same thing is true if this electron wants to move from B to C, then this C molecule should have a redox potential that is greater than 300. Let's suppose 400 millivolt. And if this electron tries to move from C to D, it should have greater than 400. Let's suppose 500 millivolt. Do you know that this oxygen is the ultimate electron acceptor in this electron transport chain? So the redox potential of the oxygen should be the highest in this total transport, and that is true. The redox potential of oxygen is plus 813, that is the highest redox potential in this electron transport chain. So this is the very basic idea you have to understand before you go to the details on how this electron actually moves. This idea, the redox potential or the electron affinity, is very important, because here you will see so many different type of prosthetic groups are present through which the electron actually moving, but this type of movement is unidirectional. How this occurs? Because the molecules have higher electron affinity or redox potentials. That's why it is called downhill movement. In my transport lecture, I have already discussed about what is downhill movement and uphill movement. Let's suppose here another time, if someone try to climb a hill, it requires energy. If someone tries to climb a hill, it requires energy, because this type of movement is called uphill movement. It requires energy. So, but if something falls from the hill, it doesn't require any energy, because it has gained actually the energy from during this its climbing, or actually it is actually gaining the energy from the height. So this type of energy when movement when there is no requirement of energy is called downhill movement. So this electron actually flow like a water molecule, that water actually flow from the hills. So it doesn't require any energy, because the molecules from where it is actually transported, each and every molecules, the immediate molecules that actually moving has the highest reduction potentials. So this is one important basic concept about this electron transport chain. Now I will talk about the proton motive force, the basic concept of proton motive force. Okay, now let's talk about proton motive force. So proton motive force is actually generated by the pumping of protons from complex, this electron transport complex, like complex 1, complex 3 and complex 4. The complex 2 do not transport any protons, so it will not actually helps in the generation of proton motive force, but complex 1, 3 and 4 actually helps in the proton motive force, because they actually transport or actually remove or pump protons during the electron transport. So the proton motive force, the basic idea about, you have to understand this, that I have mentioned in my previous class also, from the complex 1, 4 protons actually come out during a pair of electrons when moved from this complex. So from complex 1, let's suppose this is a complex 1, complex 2, complex 3. Okay, when electrons, a pair of electrons, because these NADH have one pair of electrons, when a pair of electrons move from these 3 complex, let's suppose this is a complex 1, complex 2, sorry, complex 1, 3 and 4, complex 1, complex 3 and complex 4. So when a pair of electron moves from these 3 complex, 4 protons actually released from complex 1, 2 protons actually released directly from this complex 3, but another 2 protons actually released due to co-Q. That means the ubiquinone contains the 2 hydrogen. When it is get reduced, the ubiquinone have this co-Q have 2 hydrogen atom, so it will release subsequently. So actually from the 3 complex, 4 protons actually released, and from the complex 4, 4 protons actually released. So but the complex 2 doesn't actually participate in this proton pumping, so it will not generate proton motive force. Now the theory is about that this is the matrix region, this is the matrix, and this is the intermembrane space where the protons actually intermembrane space. Okay, so what is happening here, the protons, as the proton starts to move from matrix to the intermembrane space, the charge of this matrix gets negative, because now in the intermembrane space there are so many protons are there. So the pH also gets actually changed. This is called the proton concentration gradient. So the proton motive force has 2 components. One is called electric potential gradient. Electric potential gradient, because we know when some protons or charged particles actually move from one side to another side, it will generate electric potential gradient. So here will be a electric potential will be generated like this, plus or minus I am showing here. Also a proton gradient will be generated, proton gradient. So if we think about these 2 components, this is the electrical property and this is the chemical property, that both actually contribute in the formation of proton motive force, that actually helps in the generation of ATP. So here what is happening, as the protons are actually coming out, the intermembrane space pH will decrease, the pH of the intermembrane space will decrease, and the matrix pH will be increased, and the potential difference, electric potential difference, you have to calculate. But as the mitochondria is so tiny, you cannot put electrodes directly. So scientists have performed indirect experiments where in a mitochondria that is actually good in condition, or you can say respiring mitochondria. So in a respiring mitochondria, they take radioactive potassium ions in the medium and a chemical called valinomycin. Valinomycin. This chemical is very important for this experiment. So I am mentioning another time, as the mitochondria is tiny in structure, you cannot put electrodes directly, so you cannot measure the electric potential gradient directly from a mitochondria. So you have to perform a indirect experiments, and scientists have performed a very clever experiment that they took the respiring mitochondria, they took actually radioactive potassium ions and valinomycin. This valinomycin is important because this valinomycin is also known as ionophore. Ionophore. What does it mean, ionophore? This valinomycin is a lipid soluble molecules. So scientists have taken the liposomes, where all these complex, let's suppose complex 1, complex 2 and complex 3 all are present. Okay, this all complex are present in these liposomes. This is a membrane bound region. So here what happens, the inside actually works like a matrix, and the outside, the medium, works like an intermembrane space. So when they put radioactive potassium, then this radioactive potassium cannot enter inside this membrane, because this is impermeable for all ions. Only for the protons it is permeable, because protons actually coming out from this complex. Protons can come out from the complex, but there are no other transporter present to transport these potassium ions. Now they take the advantage of valinomycin ionophore, that is a lipid soluble molecules and also can bind with these ions like the radioactive potassium. Let's suppose this is actually the valinomycin. Now this valinomycin can attach with these ions and can actually transport this molecule potassium ions inside the matrix. As I have mentioned, when protons are actually coming out from the matrix to the intermembrane space, the inside of the matrix becomes negatively charged. As more as the protons are actually pumped out from the matrix, it will get negatively charged. So there will be a common tendency of these protons, or the potassium, to come inside into the matrix. So when valinomycin attached with this, as this is the lipid soluble molecule, this is the lipid soluble molecule, so it's called ionophore. So it can actually enter inside the matrix, and scientists have found during the equilibrium conditions, when there is a equilibrium conditions, they found that the inside potassium that is inside in the matrix and the potassium that is outside in this intermembrane space, let's suppose this is actually media, they found 500 times difference. So if we put this the value 500 in the Nernst equations, we will get the electric potential. The electric potential is equals to minus 59 log this K in by K out value. So we will get minus 59 log 500. There is a 500 change, so we will get approximately minus 160 millivolt. You will get 160 millivolts. So I have mentioned that in the proton motive force there are two components. One is called electric potential gradient and is a proton gradient. This is the electric part of the constituent, and this is the chemical part, proton gradient, that means the pH difference. So at first you have seen that there is no direct way to put the electrode in the mitochondria, so there is an indirect way that they take radioactive potassium ions and a molecules that is ionophore, that can actually lipid soluble molecules can helps in the entry of this potassium ions into the matrix, because this is a negatively charged. And when there is a equilibrium conditions, there is no net flow of potassium and there is no net flow of hydrogen. In that situation they found that there is a 500 change or difference in the potassium in and out. And if we put the value in the Nernst equations, we will find that the electric potential, this E for electric potentials value is minus 160 millivolts. Now During these transportations, there is a 1 pH difference occur, approximately 1 pH difference occurs, and the value of this 1 pH is approximately minus 60 millivolt. So if we put this value and add this value with this 160, we will found approximately 220 millivolt will be generated by proton pumping from this complex 1, 3 and 4, and this is actually helps in the generation of proton motive force. So this is all about the basic concept of proton motive force and electron transport chain. In my subsequent classes, I will talk about in more details about how actually electrons are transported from complex 1, what are the constituents that actually helps in these transportations, and all the complex 1 to complex 2 and complex 3 or 4. And ultimate, I will talk about an enzyme called ATP synthase that helps in the ATP generations. So hope this video will help you. Thank you for watching and always keep learning.